Let's say you have some money in a bank account that earns 5% interest. Let's let x naught be the initial amount of money in the account. X1 is the amount after 1 year. X2 is the amount after 2 years, and so on. Now, because the account earns 5% interest, we know that x1 is 1.05 times x naught. And similarly, x2 is 1.05 times x1. And if you substitute that first equation into the second equation, then you get x2 is 1.05 squared times x naught. And then we could do the same thing for x3. x3 is 1.05 times x2. And if you substitute in the equation for x2, then you get 1.05 cubed times x naught. And I think that this is already enough that you can see what the pattern is. What I want to draw your attention to is the fact that there are two different ways of talking about this system. The first way is to describe the system as a process, where at each year, the amount of money in the account is 1.05 times the amount that was in the account the year before. Xn is 1.05 times xn minus 1. And what's interesting about this is that it's a process that repeats over and over again. In this case, the process is just multiplying by 1.05, but you can think of that as a transformation. And what happens here is that the transformation's output gets plugged back in as the input, and it repeats over and over again. This type of a process, where you have a transformation that feeds back on itself, is called a dynamical system. So the other way to describe this system is what I would call the description as a result. And this is the equation that xn is 1.05 to the power of n times x naught. This type of formula would be the solution to the dynamical system. For example, if you wanted to figure out how much money is in the account after 30 years, this is the formula you would want to use for that. Now, there's also a continuous version of this same problem, where the interest is compounded continuously. So again, we'll let x naught be the initial amount of money, but now, instead of having x1, x2, and so on, we would describe the amount in the account by a function of t, where t varies continuously. Now, this is something that I'm sure you've done in your calculus classes, so I don't really have to explain where it comes from. But in this case, the process is given by a differential equation, where x prime of t is the interest rate times x of t. And then when you solve this differential equation, you get the result that x of t is e to the 0.05t times x naught. So you can see that dynamical systems and differential equations are very closely related. The main difference is that differential equations have a continuous time variable, whereas dynamical systems have a time variable that increases by discrete amounts. But they both can be useful ways of describing systems that appear in real life. Now, what we just saw was the one-dimensional case of a much broader class of dynamical systems and differential equations that come from matrices. So let's say you have an n by n matrix A. Well, then we can use A to produce a dynamical system where we keep multiplying by A over and over again. And in this case, the inputs and the outputs would be n-dimensional vectors. And so the idea is that we would set x naught to be the initial vector, x1 to be A times x naught, and so on. And so in general, the process is that xn is A times xn minus 1, and then the solution is that xn is A to the n times x naught. So this seems pretty straightforward and not any more complicated than the simple example I showed you earlier. Except there is one thing. How do you calculate A to the n? I mean, you could multiply A times itself n times, but what if n is 1,000 or 1,000,000? Do you really want to do that? So it would be great if we could figure out how to calculate A to the n efficiently. And in addition, there are other questions you could ask about dynamical systems. One question people ask is, are there equilibria? An equilibrium would be an x vector such that when you multiply A times x, you just get the same x back. Note that this is different from ax equals b because the x that you're solving for is on both sides of the equation. So another question you could ask is, are there periodic solutions? So this would be something where maybe a times x is not equal to x, so it's not in equilibrium, but if you keep doing the process over and over again, then eventually you get back to where you started. Like maybe you go around in a circle and eventually you come back to the same place that you started. Another question you could ask is convergence versus divergence. So there would be some x naught values where the solution converges, others where it diverges, and figuring out which one is which can be an interesting question. With some dynamical systems, this can be a very interesting question, and this is actually where fractals appear. We're not going to get into that in this class, but I just wanted you to know that dynamical systems is a pretty deep subject where you can go pretty far. So you could also use the matrix A to create a differential equation. So again, you would have some initial vector x naught, and then what you'd be looking for is a vector x, which is a function of t, such that x prime of t is equal to a times x of t. So the big question here is, how do you solve this? If you tried to superficially apply what we did with the bank account problem here, then it would tell you to take e to the power of the matrix A. But what is e to the power of a matrix? Okay, so there actually is a way to make sense of what e to the power of a matrix is, but that's for a more advanced linear algebra class. So for us, the question is there a more down-to-earth way of solving it? Okay, so these equations that involve matrices, they're kind of deceptively simple looking, but I want you to see what happens when you write them out more fully. So let's look at the case where A is 2, 1, minus 1, 2. So when you write out the differential equation x prime equals a times x, this is what it looks like, but now you can actually do the multiplication on the right. And so what you end up with is a system of two differential equations. There's one equation for x1 prime and another equation for x2 prime. But what you can see is that there's interaction between the two. x1 prime depends on both x1 and x2, and so does x2 prime. So this is what's called a system of linear differential equations. And whenever you have a system like this, you can repackage it as a differential equation involving a matrix. Systems of differential equations are used to describe situations where there are different things interacting with each other, which is basically every situation ever. So like some examples that I've seen include predator-prey models, models for disease spread. I've seen interactions between neurons in the brain modeled by systems of differential equations. And then in physics, basically everything in physics comes down to force equals mass times acceleration. Acceleration is a second derivative, but it's always possible to take equations that involve second derivatives and rewrite them as systems of equations that involve first derivatives. And so that means that a lot of physics problems can be solved using systems of differential equations. So I wanted to end this lecture with an example of a dynamical system that can be used to analyze the structure of the internet. Of course, the internet is huge, so to illustrate this for you, I'm going to pretend we have a miniature version of the internet. So let's say that this miniature version of the internet has 5 web pages. Now these pages might link to each other, and so we'll draw an arrow from one page to another if there's a link. So for example, this arrow means that page 1 links to page 2. And then here are some other links. And then the question is, what are the most important pages on this internet? One way to answer this question is to imagine a dynamical system where someone is randomly clicking on links and think about how likely they are to end up on certain pages. And so we'll create a matrix that describes this system. The idea is that each column tells you the probabilities of ending up on the different pages if you're on that column's page and you randomly click on a link. So let's say that you're on page 1. Page 1 links to page 2 and to page 3. So if you randomly clicked on a link from page 1, you'd have a 1/2 probability of ending up on page 2 and a 1/2 probability of ending up on page 3. And so this is what the first column of the matrix would look like. And now page 2 only links to page 5. So if you're on page 2 and you randomly click on a link, there's only one link there, so there's a probability of 1 that you end up at page 5. From page 3, the probabilities are 1/2 of ending up at 1 and 1/2 of ending up at 4. For page 4, there's a probability of 1/3 of ending up on page 1, 1/3 for page 2, and 1/3 for page 5. And for page 5, there's a probability of 1 that you end up at 4. So what this matrix does is it gives us a dynamical system for probabilities of being on any given page when you're randomly clicking on links. So to be more specific, if you had a vector where the entries in that vector were the probabilities that you were on each of the different pages, then when you multiply that vector times A, you get the new probabilities for which pages you would be on after randomly clicking on a link. And then you might expect that over time, if you keep randomly clicking on links, eventually the probabilities would start to approach an equilibrium. So in other words, an equilibrium should describe long-term behavior of the system. And I am skipping some details about, do we know that an equilibrium always exists? Do we really know that it describes long-term behavior? Let's ignore that for now, and let's just take for granted that this might happen. Well then, if that's the case, then in the equilibrium, the pages that we're most likely to be on are the most important pages of the internet. And so in this case, we can actually solve for the equilibrium. So the equation for an equilibrium is a times x is equal to x. And to solve this, the first thing we'll want to do is move the x to the left side of the equation. And then we can note that x is the identity matrix times x. And now we're in a situation where we can factor the x out. And we get the equation a minus I times x is equal to 0. So in other words, we're looking for the kernel of a minus I. So here's a minus I. It looks the same as a, except you have minus 1s down the diagonal instead of 0s. And now, at this point in the semester, you know very well how to solve for the kernel of a matrix. You put it into reduced echelon form, and you solve the homogeneous equation. And in this case, what you get is that there's one free variable, and the solution is the free variable times this vector, 1/2, 5/8, 1/4, 9/8, and 1. Now, if you want to interpret this as probabilities, then there's a good choice for t, which is the one that makes the numbers in the vector add up to 1. So you have a total probability of 1. But for our purpose, all that really matters is which numbers are the biggest, because those are the ones that correspond to the most important pages. And so because 9/8 is the biggest number, that tells us that page 4 is the most important page. And we can even get a ranking of the pages. From most important to least important, there's page 4, page 5, page 2, page 1, and then page 3. And that's how this works. It's pretty straightforward linear algebra, right? A few years ago, there were some guys who started a company based on exactly this idea. Their names were Larry Page and Sergey Brin, and the company was Google.